Hi, this is in this lecture we are going to be seeing an example for random forest classifier. The problem given for this particular classifier is that we have information about a few potential bank customers, and the goal is to predict whether these customers will actually buy a new product. So you have a list of potential customers to whom you want to sell a loan product, and you want to predict whether these guys will actually go and buy the product or they will not buy a loan product. And the information gives you actually some attributes about various bank customers, information about them, as well as information about the previous loans they have taken and whether they have properly paid those loans and stuff like that. The techniques used are random forest. We are going to be also doing training, testing, confusion matrix. In addition to that, we would be doing some more pre-processing. We would be like creating indicator variables. We would be using binning, and we also would be doing variable reduction. To start with, let us load the Panda libraries that are required for this purpose, and then we're going to be changing the operating system working directory to that of random forest. To start with, we are going to be reading this file called bank.csv, and then we start analyzing what does this bank.csv contain. And you see that it has got a number of columns in there: age, job, marital status, education, default, whether the person defaulted an earlier loan, the last loan balance, whether they had housing or not, whether they had previous loan or not, how they were contacted, when they were contacted, like day, month, duration, and stuff like that. When you do a describe, again the describe gives you a lot of information about the numeric columns that you have in the data set. And pretty much you can immediately see that, let's say, the age is between 10 and 87. So that range looks okay. The balance is between a minimum of minus 3313 to 71,188. So you might ask if a minus 3313 is a valid balance. Maybe in this bank, yeah, they allow you to keep negative balance. So it might still be okay. The number of days is between like 1 and 31. So that makes again sense. It's the number of the days. This is actually the day of the month. So 131 to 31 is a good range. So that way you look at and see the data looks pretty clean. There doesn't seem to be any kind of issues or errors in the data. Let's take a sneak peek at the data, the top head, and the job is like unemployed, services, management, marital status is like married, single, education like primary, secondary, tertiary. So it's got information about the customers in general. So what kind of data transformations we want to do is we want to bin the age. So age is a continuous variable here. So we want to use the cut function to actually bin the age into ranges like 1 to 20, 20 to 40, 40 to 60, stuff like that. So we're going to be first binning the age in from a continuous to a discrete variable. Then we're going to be creating dummy variables for marital. So for every marital status, we are going to be having a separate column. So that you do it by the get dummies function, and then join it with the bank data to get the final bank data. And then see, given that now you created a dummy variable for marital, you can delete the original marital variable now. Now let's look at the data and see how it looks like. So you see that the age has now become a range from 20 to 40 and 40 to 60, stuff like that. And then we see in 3 new columns: divorced, married, and single, that has been added, which actually gives a flag of whether it is 1 or 0. Once we are done with this, we want to convert since for using these ones are features, we want them to be numeric values. So we want to convert all the textual representations into equivalent numeric values. So here is an algorithm that goes into every column, checks whether that column's type is actually an object, and if it is an object, it converts it into a categorical variable, which is a fixed set of predefined values. And for each of the fixed set of predefined values, it gives an ID starting from 1, 2, 3, as many number of distinct values that are there in the column, and then puts that ID value in the column value. So it looks at each of the column, checks if it is a object or an integer. If it is integer, it leaves it out. If it is an object, it converts it into a categorical variable, and the categorical variable is then converted into an equivalent ID, or like a 1, 2, or 3, 4 kind of, depending on the number of distinct values that particular column has. So that is this code that you're going to run now. You can explore the code in detail on a self-paced mode in this case, and then now look at the data types of your data columns, and all of them are now integer. And then if you do a describe on the column, you see almost all of them have now become numbers. And you see all the columns now have a count, a mean, standard deviation, and everything. The image is kind of a little messed up here, but I think once you can do, when you do it yourself, you can explore it a lot easier in maybe a bigger screen. Once now you've converted all of them into numerical, let's look at all the correlations that the bank has. And what you would see in this data set is that the correlations are not that great at all. In fact, if you explore pretty closely, on the top, you don't see really big correlations. This is a 0.12 correlation. This is the rest of this is 0.003, 0.073, 0.16. So the correlations are not that great for age, especially when you look at against a target variable y. So y is the target variable that tells you based on previous history whether the customer bought the product or did not buy the product, and the predictors for this variable y, if you look at, the correlation coefficients are not going to be that great. And that kind of immediately tells you that the model you're building might not be accurate. So let's go and still build the model and see how well you can come up with this. Now, based on the information, you see that correlation coefficients, you see that y does not have good correlation with the number of the values that you saw there. So what we want to do is go and delete a number of these columns which do not have any kind of correlation with y at all. So you have a number of columns here: default, balance, day, month, campaign, outcome, which we are going to simply go and delete all of them. That way your data set is small, and then you can work with a smaller data set a lot more easily. Once we do this, we pretty much get down to the same process again. We separate the predictor and the targets here, and then still separate them further into the training and testing data sets using the train test split function like we did before. And then now we will look at all the shapes of these ones. You see that it is being split into as expected. 70-30 split is being achieved. Again, now you see basically now the steps are being repeating again and again. So that's what the sklearn library gives you. It gives you a standard process you can follow irrespective of which algorithm you're using. It makes life pretty easy for you to implement multiple algorithms with the same piece of code. So now let us go and import the random forest classifier, and the same steps once again. Create the classifier. When you create the classifier, you give n estimators. N estimator is basically the number of trees that you would build in this algorithm. So you tell it upfront you have to build 25 trees in order to do this prediction. So let's go build 25 trees in here, and then actually do the fit, which is to build the model. So the model is built, then go and do the predictions on the test data set. Now predictions are made, and now go and do the confusion matrix to see the y prediction. Pretty much okay. You can say that 137 and 57. There seem to be still a lot of errors in trying to predict the no part. This 1137 is the no part, 57 is the yes part. There's still a lot of errors in this case. The accuracy is 0.87, pretty high, but that is because the S number of the amount of yes, the amount of no you have in the data is a lot higher than the amount of yes here. So whatever you see here as this 1137 is actually influencing the overall accuracy numbers. But I would still worry about the 61 and 102 as to why I'm getting so much deviation in there. One possible way by which you can try to reduce this discrepancy is that when you're picking up the original data set, make sure there are equal numbers of yes and no's in the data set. That way you give equal chance for each of the type of outcome, each of the class of outcome, and then case possibly the model is not skewed towards the larger class. So that is one possible way by which you can eliminate that issue. Now that we have built the trees, let us ask the question as to, I built 25 trees and I'm getting an accuracy of 0.88 or 88%. What happens if I only build one tree or two trees or three trees? So what I'm going to be doing is I'm going to be now repeating the same exercise for different values of trees. So what this particular loop is going to do is repeat the same exercise of building a random forest classifier for the number of trees ranging from 1 to 25. The range is number of trees from 1 to 25. I'm going to be repeating the same exercise for different size of trees, and then finding out the accuracy score for each of those tree values and storing in an array. So that is what I'm going to be doing here, is repeating from 1 to 25, and then run this guy, and then finally I now get 25 different values. So that will then now go and plot all of them and see, how the accuracy changes as the number of trees increase. So what you see here, this is the final chart, is that when you start with a tree of 1, 2, that is pretty low in this case, like 87, 88%. But as the number of trees increase, you see that it is slowly stabilizing to a higher value and possibly then stabilizing here. Like after the 10th tree, you see that it is kind of almost in a straight line. So until the 10th tree, there is a slight increase in your accuracy levels. Not that much though, still a slight increase in this case. Depends upon the use case. Sometimes you will achieve very high accuracy even with very less number of trees. Sometimes again, depending on the use case, you might actually see like the accuracy might start like at 30%, and as we increase the number of trees, it may keep going up to 80-90%. It again depends on the use case, the actual input data that you're having. So it might vary depending on that. So in this case, you see how the number of trees you built impacts the accuracy levels. The more the number of trees you build, the more resources you use. So you don't want to be building a lot of trees, but you want to build enough number of trees to maintain very good accuracy levels. So that is a balancing act you can do. And this specific code that we see here can be used to figure out what would be the optimal number of trees that I would build for this given data problem. That's all we have for data decision trees. Random forest.